Following on from the previous video, we're going to try and solve the same problem, but this time use implicit differentiation. So this here is a condition placed upon us by the post office, and we're trying to maximize the volume. So we've got to find X and L where it would give us the biggest volume. Okay, so that would then take us to here. So this here is a condition placed upon us by the post office. Now, if you look at the problem, we've got X, and then L, okay, and then L here, and then L here. Well, don't forget we are varying X, so X could be 1 minute it could be a big square, or it could be a small square. But the point is that we are varying X. We are sliding X back and forth. And when we slide X back and forth, L will react accordingly. So L will be a function of X. Okay, L will be a function of X. Now, the other variable would be the volume here. We need to consider the volume. Now, as we vary the X back and forth here, the volume will react accordingly as well. So the volume here is also a function of X. Bear that in mind. Okay, so this here is a condition placed upon us by the post office. Now use implicit differentiation. This 400 is just a constant. Okay, as we vary X, remember, as we vary X here, L will react accordingly, V later on will react accordingly, but this 400 will not react as we vary X. So this is just a constant. So when we differentiate this, it will give us 0. Okay. Now L here is a function of X. So when you differentiate that with respect to X, it will give you this. Okay. Now differentiate this with respect to X, that will give you 4. Okay. So dl by dx equals minus 4, whatever that means. Okay. dl by dx equals minus 4. So now let's look at the volume now. Don't forget the volume, as we vary X back and forth, the L here is a function of X, and also the volume here will be a function of X. So when we differentiate this, because the volume here, remember we are differentiating this with respect to X. So because V is a function of X, when you differentiate it, it will be dV by dx. And now this, don't forget, this here, we are differentiating it with respect to X. And L here is a function of X. So here we've got to use the product rule. So the product rule, differentiate this, leave this the same. Okay. And then, on a separate occasion, leave this the same, and then differentiate this. That will give you this. So when you use implicit differentiation, that would then take you to here. Okay. And then earlier, don't forget earlier we worked out dl by dx. So dl by dx here is minus 4. So put that into here. Okay. So that will then give you this. So dv by dx is given by this. Okay. And now we want to know where. Don't forget, at the moment we've got a graph of volume versus X. So so we've got this graph at the moment. So we want to find out where this thing here would be 0. So set the whole thing to be 0 like this, and then add this to both sides. So that will then take you to here, and then that would then take you to here. So what it means is that L equals 2x. So what that means is that if you want to maximize your volume, make the length here twice that of the length here. Okay, so make this length here twice the length of this. Okay,